Sorry, I seem to be late for class, but it's your guys' fault this time. It's a forced digression. Don't worry. I will go overtime to make up to you. So, okay, I'm just joking. I probably won't do that. Probably not. Let me begin with a word of prayer. So, been hemmed. Dear Heavenly Father, we thank you for this day. I thank you for these students, and just pray that you guide our steps today. Help us to glorify you, what we do, Lord. In your name I pray. Amen. All right. So, I know. Oh, no. These are things I like to think and talk about, but, I mean, I entered this whole discussion with the assumption that accreditation meant academic quality. And it's taken me a few years to realize it does not mean that. It really does not. Accreditation of a university means it's financially stable.
What would your solution be?
My solution?
Mm-hmm.
Well, it's kind of like asking what's the solution for government. It only works as long as you have, people who are
willing to do it.
Ethically serious about the project. So, as long as you have most people going to university to get a degree and not an education, it can't be fixed. It can't. But that's okay. I like my job. Let's see here.
Maybe you'll leave a page.
40. I don't think so. 4793 is your top hat. All right. Let me write out the algorithm. I'll try to go fast here. Graphing rational functions. Okay, so we're given f of x equal to n of x over d of x, where n of x and d of x are polynomial. They're polynomials, okay? I want to just try to briefly describe to you the algorithm for graphing these, all right? So like here it is, step number one. Step number one, you completely factor n of x and d of x, all right? Step number two, identify all zeros of n of x and d of x and make sign chart for f of x. In other words, you put all the critical numbers on the number line, and then you put pluses and minuses like we did before, okay? Step number three, if the degree of the numerator is less than the degree of the denominator, then y equals to 0 is your horizontal asymptote. In other words, the graph is going to get drawn into y equals to 0 eventually. On the other hand, if your degree of the numerator is greater than or equal to the degree of the denominator, then long division awaits you. So you do long division, and that's not entirely true. There are examples where you can get away with not doing the long division and still get the information that you need. I'm going to make a handout for this part of the course where I'm going to put all these thoughts in one nice place for you. I was wanting to do that for the day, but I just didn't get time. I'm teaching this other course online, and it's kicking my butt. Because it turns out it's kind of hard. Like you have to think through it. What?
That was supposed to be easy.
Ah, that's true. But this is not an online course for the masses. This is an online course for one student. That's a very different thing. Like I told you, I don't disagree that the online format can be useful. But I think in terms of like mass production, it's like the quality of online tends to be lower for a class like this, right? If you take 121 online, you're not going to learn as much as you did in here, I don't think. Part of it's just that you're doing it in 8 weeks, right? And I don't think that alone is a qualifier either. I think 8 weeks can work in the summer. If you're doing nothing but math for 8 weeks, that can be a wonderful experience. I can think of no better way to spend the summer, right? You're like, he's not kidding, is he? No, I mean, like that would be an amazing summer, right? But you're focused on that one thing, right? You do an 8-week course here. Are you focused on that one thing? You are not. That 8-week course is in the margin, right? It's after fun with friends, bowling, Dungeons and Dragons, whatever it is that you're doing, you know? Let me not get into the Dungeons and Dragons again. Okay, so anyway, long division gives us f of x. You guys make me do the best digressions in here. This is definitely the best digressing class in this semester. So f of x is equal to p of x, the polynomial piece, plus the remainder term from the long division divided by d of x. If this is what happens, this piece right here is a proper rational function, meaning that the degree of the r of x is smaller than the degree of d of x. This thing right here, this will go to 0 as x goes to plus or minus infinity. And so what that means for your graph is that y is approximately p of x for x going to plus or minus infinity. In other words, this is how the graph behaves what's called asymptotically, all right? A lot of times, that p, it's just a number, and then this is just a straight horizontal asymptote, just not at 0. It could be at 1 or 2 or 3 or minus 2, whatever. So there's two cases here. Case number 1, you have the degree of numerator smaller than the degree of the denominator, easy peasy, y equals 0. That's usually what happens. But if the degree of the numerator is greater than or equal to, then we got to think about it, okay? Then step number 4, graph. Graph it. Now, let me kind of dig into the details there, though, okay? So, for critical number C, in other words, it's 0 of n of x or d of x, all right? There are different things that could happen. There's a bunch of different cases, okay? So let's sort through those cases. I'll start with the 2 easiest cases. Yeah. So case number 1 is that x minus c is factor of n of x only. All right, only n of x. It just appears in x and n in the numerator, but that's it. If that's the case, then you've got an x-intercept of c0. Simple as that. All right. Case 2, if you have x minus c is factor of d of x alone. All right. If x minus c is only a factor that's appearing in the denominator, what that means for the formula is when you plug c in, you're getting division by 0 unopposed, which makes the formula blow up, which means that x equals to c is a vertical asymptote for the graph, okay? So obviously knowing where x-intercepts are and knowing where vertical asymptotes are, these are going to be integral to making the right picture, right? And then case 3, this is where it gets messy. If x minus c is factor, of both n of x and d of x, then we got to think. There are 3 subcases here. All right. And some people would make 2 subcases, but those people are mathematicians, so we don't care about them. So, a bunch of jerks. That's not true. Okay, so if the order of x minus c is same in n of x and d of x, then c comma the reduced function of c is whole in graph. All right, so you get a hole in the graph if their orders are equal. If the order in n of x is larger, then c comma 0 is whole in graph. So the hole is actually at the x-axis. All right. And then what's the other case? The other case would be if the order in d of x is larger. Or you could say the order in n of x is smaller. Yeah. Same thing. So in other words, if the denominator wins, if the denominator has more copies of x minus c in it, again, it's just a vertical asymptote. Okay. Let me attempt to do easy examples of these. So far, every time I try to do an easy example, it somehow becomes uneasy. So, I'll get out of the way here in just a second. Since I came all the way back here, I'll do that, but thank you. I was mostly forcing myself to get out of the way so people could finish writing. All right. So this one is pretty easy in the sense that, like, step number 1, completely factor. It's already completely factored, right? Step number 2, what are the zeros? 2, right? So if you plug 3 into it, you get positive. You plug whatever less, it's negative over here, you know? So what's the deal? We have, which case are we in? So if you look at n of x and d of x, what are they here? But it's not even. See, because there are 1, 2, 3 copies, which means we have an odd number of x minus 2, so flip signs. Good question. So n of x has 2, right? D of x has 2. The order of x minus 2 is 1 in the top. The order of x minus 2 is 2 in the bottom, right? So in this one, the denominator wins.
Because of power.
Because of the power 2, right? So the graph here is pretty simple. In fact, you can't tell the difference. This is kind of a funny example because you have y is equal to, x minus 2 over x minus 2 squared, right? That is equal to 1 over x minus 2 for x not equal to 2, right? Like, I can cancel the factors as long as it's x not equal to 2. So this is a funny example in the sense that this is just a more complicated way of writing the formula for that. We already know how to graph that anyway, right? We just take the reciprocal graph and we shift to right, right? Remember? The transformation of graphs. So we take the reciprocal graph and it just shifts to right. So this is the graph we're looking at here. So, I don't know. This example might have been too easy in some sense. Let me try another one here. what if we had f of x equal to x squared plus 2x plus 1 squared over, oh, I don't know, x plus 1, let's say,
Cube.
sure, I'll take a cube. Why not? This is a pretty silly example. So we completely factor. What is x squared plus 2x plus 1? So that's x plus 1 squared, right? OK, so what we're really looking at is x plus 1 to the 4th power upstairs divided by x plus 1 cubed downstairs, right? So what's going on here, all right, is that you have a critical number of -1. You have order 4 on the top. You've got order 3 on the bottom, which means we're going to have a whole. And so what does this simplify to, by the way? This is just equal to x plus 1 for what? X not equal to -1, right? So I'll get to the point here. There's no point in for me. I don't think there's much to be gained for me making the number lines here. I'm just going to show you the answer. So what is x plus 1? What's the graph of y equals x plus 1? It has a y-intercept of 1. It's got a slope of 1, right? So it's like this. So what you're looking at here, and there's a hole in the graph, right? Where? The hole in the graph is at here. So this is the graph of that rational function.
Wait, how did you know?
That's at -1, right?
Yeah, -1. How did I what?
Is it that because it's the critical number, is that in the whole is?
Yeah, the critical number here is -1. And because the degree of -1 upstairs is larger than the degree of -1 downstairs, that means I have the x-intercept is a hole in the graph. But again, you can just look at this like by algebra, just common sense also, right? Because this simplifies. I can't always do this kind of calculation so easily, but this one allows for it. Like I can just cancel out and say, well, this formula is y equals x plus 1 everywhere except for the whole, right? So I know how to graph. You guys know how to graph y equals x plus 1, right? So this is, technically, this is an example of a rational function with an oblique asymptote, which means that the asymptote is like a line. But this is a kind of stupid example. So let me try to make something less stupid. OK, so let's look at f of x equal to, oh, I don't know, x squared minus 5x plus 6 divided by, let's say, oh, I don't know, 4x squared minus, oh, my bad. No. What am I doing? I have this habit of making overly complicated examples if I'm tired. Let me not do that. X squared minus 1 there, let's just cut our losses right there. That's a good place to stop. All right. Let's try this one here. So, okay, we need to completely factor. So what's completely factoring look like here?
X minus 1
X minus 1
Plus
times
5.
x.
plus 6, sorry.
Uh-oh. Plus 6?
Yep.
But that's not. Oh, tell you what. You know what? There you go. Is that better?
Okay.
There we go. Okay, feel better? That is what I intended anyway, so it's good, it's good. I was trying to make it minus 1 and minus 6, but I should have had a minus 7 there to make that happen. My bad. Anyway, so this is fine. I changed this to a minus, guys, if you didn't pick it up on. I changed that to a minus so the factoring makes sense now. And I mean, we could factor it when it's ugly, but let's try to focus on one hard thing at a time. Let's just try to make the factoring easy and the graphing the focus, right? Just cancel out the x minus 1. Well, okay, that's the thing. You can, but we need to understand what we're doing, okay? So my number line, what are my critical numbers? Minus 6, negative 1, and positive 1, right? So let me just kind of put a summary up here. 1 is a hole, one hole in graph. If we look at the critical number of minus 6, it's x-intercept of minus 6 comma 0 because it's unopposed up here. And c equals to minus 1 is, it's down here, unopposed, so it is a vertical asymptote. Yeah, what'd I do?
You need to flip the signs up top for it to be -5.
Oh. The reason I did that is because I've already written all of this. So I want to keep them where they are. That's okay. Sorry.
So are you getting what you wrote in red from the subthings over there?
That is true. Hey, as I planned it, yes. But yeah, that's, so, well, not entirely. I mean, so I'm really using 1, 2, and 3. Mostly, so like the number 1 I used to get the comment. So like number 1 applied because x plus 6 is only there. It's not in the denominator, right? So that's like number 1 tells me x-intercept is 0, right? Okay. Number 2, to be fussy, I applied number 2 to get my vertical asymptote of minus 1. See, because this x plus 1 is unopposed downstairs, right? And then number 3, part 1, gives me hole in the graph because I've got an x minus 1 upstairs and downstairs. What is the reduced function is the question though, right? So where is the hole? Okay, so the reduced function, that is the thing you guys wanted to do at the start of everything, just cancel the factors. So cancel out the x minus 1, we're left with x plus 6 over x plus 1. All right, that's the reduced function. You cancel out the factors corresponding to the hole, and then we plug in 1. We get 1 plus 6 over 1 plus 1, also known as 7 over 2. So the hole in the graph is actually at 1, comma 7 over 2. That's the hole in the graph. It's there. That's where it is. All right. All right. Let's try to graph this thing. Where was my vertical asymptote? Minus 1. Okay, so we've got one of those here. And I've got, what happens at 1? Oh, the hole in the graph, that's right. So that's kind of sort of here-ish. Okay. I'm going to regret putting that label there. Oh, what have I not done yet? The signs, right? I need to do that. So we start out what? Start out positive in this one. We get to 1. How many factors corresponding to 1 are there? There's the x minus 1 and the x minus 1. Those are the ones you got to look at, right? So there's 2 of them. So that means we stay plus. We don't flip. Now when we get to minus 1, that corresponds to the x plus 1 factor, of which there is just 1. So we flip. Then you get to minus 6. There's just this x plus 6 factor here. So we flip again. All right. And so there is a x-intercept at minus 6, yeah. Oh, and before I graph, there's something else I should do. What about, I'm not very good at following my algorithm in order sometimes. I kind of jump around, my bad. But 3, we need to think about 3, you know? Is the y equals 0 the horizontal asymptote for this problem?
If the degree is greater than the degree of the denominator.
So,
No.
no. Right. So there's various ways to go here. If you want to, you can actually use the reduced function to figure out the horizontal asymptote, because the reduced function is what the function looks like away from the hole in the graph. And so when you're thinking about what does the function look like asymptotically, you can think about the reduced function. And it's oftentimes easier because the reduced function has lower order, right? Like, which is easier to think about, this function or the original one? Like, obviously the reduced function is easier to think about, right? So this one here, since I like you guys, I'm going to show you a trick. This is x plus 1 plus 5 over x plus 1, which is x plus 1 over x plus 1 plus 5 over x plus 1, which is equal to 1 plus 5 over x plus 1. Or I could do the long division. The long division way of thinking about this, I'm dividing x plus 6 by x plus 1, right? So I put a 1 up here. That brings down my x plus 1. I subtract these guys. I get 5. And as such, I get exactly to this result. So long division also reproduces this. The point of this is from this I see, aha, y equals 1 is the ha. Haha. Yeah, like, stop being an idiot. I can't. It's how I was raised. See here. That's not true. This isn't on my parents. My parents were doctors, not mathematicians. Let's see here. So 1, although my dad was a math major, fun fact. Rest his soul. But we never really had an honest conversation about like higher math. He was a math major, but just for the purpose of getting to medical school.
Really?
Yeah. It's a pretty good resume booster at that time for sure. And I mean, it worked. He went to medical school.
Did you ever talk about math with him?
Not really. I mean, he wasn't bad at math. He just didn't care about it that much. Yeah.
So what makes 1 the horizontal asymptote?
So when we look at the reduced function, which is equal to the function for large x, we see that the formula reduces to 1 plus something else, which goes to 0. So whatever this piece out front is what's going to dominate for like large values. So that's the constant. It's the horizontal asymptote. Now, listen, there's another way to think about this kind of problem. This will be on the sheet. I'm telling you guys now since I like you, most of you. Let's see here. You've got x squared. I mean, there's another way to look at this. Many books would cover it like this. X squared plus 5x minus 6 over x squared minus 1. You're looking at this, right? This is what we're graphing. And so when you have this kind of thing, when you have an equal degree in the numerator and the denominator, there's a very simple rule. It's just the ratio of the leading coefficients that's going to be your horizontal asymptote. That's all that there is to it, really. See, because you could look at it this way. If you divide the top and bottom by x squared, we get 1 plus 5 over x minus 6 over x squared divided by 1 minus 1 over x squared. So what I did there is I divided the top and the bottom by x squared. Yeah. And so if you think about this, what happens as x goes to plus or minus infinity, all of these terms with division by 0, I mean division by a really large positive or negative number, they just like they're gone, they're nothing. All that remains is the ratio of the leading coefficients.
If there was a 2 on top, it'd be 2.
Yeah, if you had y equals, 13 x to the 17th power plus x minus 2 divided by 12 x to the 17th power plus x squared minus 42, then this will have a horizontal asymptote of y equals to what?
13 over 12.
13 over 12, yeah. Now, this is not something that is going to appear on your quiz or test. Well, I mean, probably. Well, this question alone perhaps would, but I wouldn't ask you to graph that. Why? What would step number 1 be for graphing this thing I just wrote on the board? Yeah, we'd have to completely factor the numerator and the denominator. Have we ever factored a 17th order polynomial?
Nope.
Do we want to start now? No?
Can you show us an example?
Let's do it. No, I'm done. No, let's move on.
You want me to factor a 17th order polynomial?
Please do not.
It's tempting. If you had... No, I mustn't.
No,
I mustn't. I feel like this is a trap. Let me finish graphing this and then I'll do it, okay? Okay, so we have everything we need. We've got our horizontal asymptote of 1. We figured out this is the x-intercept. That's the hole in the graph. Listen, the way we graph, the only way you can cross 0 for the graph is at critical numbers, right? That completely guides our thinking. So, and we have to get sucked into like we're eventually drifting into that 1, like that. This is a vertical asymptote, so that means that you got to go down, 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 or up, 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 depending on whether you're positive or negative. Here we're negative, so we got to go down, right? Over here, it's got to do something like this, all right? And then what happens is it just kind of drifts into the horizontal asymptote like that, and that's the graph. It's just that.
Does it shift a little bit down, or does it all the same?
The bend in the graph there is just a consequence of me not having good scaling on the board. It's not meaningful. It probably would be much more like continuous if I was graphing it properly. I was asking the last class how many of them had like art class in high school. Show of hands. So I should put something on the test where I have like, I have had art class in high school versus I have not. And for those of you who have had, I should like grade the continuity of your graphs more severely. Like I expect like this, I would take a point off. Like, come on, like it doesn't, come on.
They get bonus points if they do
It's not cool, right? And so they get bonus points. What are those? But no. All right, let's do another example. Well, hey, I'm doing better in here. Last class I got 2 examples for the whole section, the whole period. Like these, if you're not careful, these examples take forever. And don't even get me started about the first section in here. You should see the example I did in the first section. Oh, it was horrible. Example 4. All right, here we go.
Not going to factor the 17th order.
Y equals f of x equal to, if I have time. If I have time after this example, I will factor a 17th order polynomial for you. Yes. All right, here we go. They're so mean. So mean. I like it. All right, so let's see here. So let's suppose we've got x squared plus 3x plus 2 times, oh, I don't know, x squared minus 1 divided by, let us say, x minus 3 squared. And, oh, I don't know. What do I got? I got 4th order on the top, right? So let's say x plus 6 squared there. Okay. We're gonna use our shortcut, right? Let's use the shortcut here for one thing. So like what goes on here is, if you look at it, multiply it all out, right? We're gonna have like x to the 4th plus stuff, right? And then downstairs, we're going to have x to the 4th plus stuff if we multiplied it out, right? So just leading comment, y equals to 1 is our horizontal asymptote for this problem, okay? Let's just get that out of the way at the start for this problem, okay? We don't need to do long division. We don't want to do long division if we can help it, all right? There are other problems where the long division is much more interesting. Is that your question?
I was going to ask, like, is that going to work on everything?
No, no, it won't. So, example 5, if we had y equals f of x equals to, say, x cubed over, x minus 1, you want to graph that, right? You're like, so we have to divide the x minus 1 into it. And let's see here, so then we get plus x plus 1 if I didn't make a mistake, I think the remainder is 1. So you see you have f of x equals to apparently x squared plus x plus 1 over x minus 1. Now this one, what you do is you look at this, you complete the square on this thing. See, that is x plus 1/2 squared plus 3/4. And so that's a parabola which opens up. It has a vertex of minus 1/2 comma 3/4. Right, so like my parabola, here's my parabola, all right? The function has a vertical asymptote at 1, like that. And if you look at the formula, it's, well, fine, I make my sign chart. I've got 0 and 1 for critical numbers here. I got pluses, minuses, and then pluses again, I believe. Plug in 2, I get positive. Plug in like a half, you get a negative. If I plug in like a negative number, I get negative over negative, which is positive. Okay, great. So the graph of this thing, I'll make blue. It's got an x-intercept of 0, right? Because the x cubed upstairs, it's got that x-intercept, right? And it's got a vertical asymptote of x equals to 1. So it does something like this. All right? And then it gets dragged back in to this parabola long term. And on the other side, terribly poor planning on my part, I'm about to do something very, very hideous, so my apologies.
Oh, it's awful.
Yep, it's horrible. So it's negative on the other side, right? But then it's going to eventually drift up into this parabola. So like it's getting dragged into the parabola asymptotically. So like the function goes into the parabola. It's got a break at x equals to 1, but then like asymptotically it's drifting into the parabola. This would be a parabolic asymptotic. No one in their right mind would put this on a college algebra test. All right? You're like, well, you seem a little crazy.
But I will.
No, I'm not going to do that. No. So I think the worst thing I would ask you to graph conceivably would be like an oblique asymptote. And even that I would regret my life for doing. So, okay. Most likely I'll ask you to graph something with horizontal asymptotes because that I can actually grade. Okay, so that answers your question though. See, the long division, like I can't just use the ratio of leading coefficients thing for this one, right? I can't use the ratio of leading coefficients for this one. I mean, like the p, this is the p of x I was talking about in the algorithm over there. And so that's what the graph goes to eventually. Anyway, Okay, so
17th order.
back to the, I still need to finish this example. So we've completely factor, right? We've got what? X plus 1, x plus 2, x plus 1, x minus 1, x minus 3 squared, x plus 6 squared. What happens? We've got x plus 1 2 times, x plus 2, x minus 1. All right, so let's sort it out. What do we got here? What's our first? Minus 6, right? What's next? Minus 2? What's next? Minus 1? What's next? 1, right? And then 3. Okay? And the signs? Because I keep making my examples boring, it starts out plus. At 3, do we flip signs or keep it? Keep, because we got x minus 3 squared. So we keep the plus. How about at 1? At 1, flippy flop, yeah. At minus 1, corresponds to x plus 1 squared, so we keep it. At minus 2, flip. At minus 6, keep. Yeah. Okay, is there any sharing? Like the zeros for the numerator, the zeros for the denominator, they're distinct, right? So this example is easier than some of the ones I've done today because it doesn't have the hole in the graph problem. This stuff right here is the tricky part, all right? If you don't understand this, it's kind of okay, but you must understand this part. This is essential, okay? Like, you must at least understand that. I mean, try to understand everything. Where's my vertical asymptotes at? So I already said that we've got a horizontal asymptote of 1. Where are my zeros at? I've got a 0 from the numerator ones, right? So I've got a 0 at minus 1. I've got an x-intercept also at minus 2. I've got an x-intercept at 1. I've got vertical asymptotes from the ones in the denominator. There's 1 at minus 6. And there's 1 at 1, rather at 3, right? The rule for bouncing and crossing is like the same for x-intercepts as now as it was for polynomials, actually. It still bounces at, we're going to see it still bounces when you have like a squared factor, right? Okay, so here it is. Plus, so we got something like this here, like that, and it stays, it's like a volcano. We go down through here. We got to bend back. We bounce off that though, right? So we bounce, stay negative, and then we're going to cross at the 1. Then we go up here like that, and then volcano back down. There you go. That's the graph. And now I am obligated to factor a 17th order polynomial.
Yes.
You have 60 seconds.
I have 60 seconds. Here we go. Why? Are we? Did you pan over here? I don't want to miss this. So x to the 17th minus 1. I can factor this one. Here's how it factors. X minus 1 times x minus omega times x minus omega squared times x minus omega cubed times x minus omega to the 4th power x minus omega to the 16th power. Here omega is equal to the e to the 2 pi I over 17. In the complex plane, they look like this. They're like symmetrically situated around the origin. The roots of this are the 17th roots of unity, which are these things. So, be math majors. I will teach you this. No? Someone here must want to be a math major. No? No?
Computational math.
Computational math major.
Joe.
Well, I am teaching the 423 in that, so you had me for that one. Yeah. Oh, you can